this session, just so you're aware. And secondly, I hope you're all home having a safe snow day. If you had to come to campus, that you arrived safely. But the number of emails I received this morning suggesting that travel was a little bit unsafe, I wanted to make sure we still had a chance to meet. So first, a couple of things. My camera is off just so I can share screen. I do want to know that you're hearing me okay. So can you either give me a thumbs up in the chat quick or just turn your mic on? Let me know someone and let me know that you can hear me. Awesome, thanks. Hey, I see in the chat we can hear each other. Awesome. Some of you look like you're raising your hand, also giving me a thumbs up, so that's all cool. Hey, I just wanted to get together and kind of go through some of the homework problems that ALEKS is presenting you. I know that it's not due until early next week, but we do have an abbreviated schedule because of Thanksgiving. So our goal today is just kind of touch base and see how your redox reactions, a little bit of electrochemistry. And so one of the tool pages I have out in handy is my reduction table. But I have to be honest, if you don't have yours out, that's really fun because I've done the hard work and looked up the values for the problems I chose. But just to be aware, that is a test-taking tool page. I know ALEKS will have a data link that you can click and bring up this table as well. But you might find it handy just to have it on your desk so that it saves you time when you have to look up anything. I also have a calculator because I am not exceptionally gifted in mental math, so I have to have my calculator out as well. So if we're ready, why don't we go ahead and take a look at a first question. And I know that I just screen captured what you will see in your ALEKS. So I'm just going to take a look at the picture. Here I'm noticing that I'm given a kind of a picture of a wet cell, if you will. So I look at this and say, okay, this is going to be something about looking at a battery. And I'm just going to draw this with you and kind of talk through, whoops, I keep bringing up the keyboard, kind of draw through what I see. So go ahead and draw this part with me. I notice that here I have, whoops, I'm not being able to draw. Let me kind of work that out. Here I am. There I go. Somehow I have to get this working. Darn it. There. Oh, Linda. So some of my touch screen is working and some is not. All right, here I'm just kind of figuring out what I'm looking at. Notice that I have just one container, and inside of that container, I see that I have two electrodes. And those two electrodes are giving me kind of a different look than two different beakers that we see in a voltaic cell. One other thing I notice is that up here, I see that I have a positive and negative electrode that these graphite electrodes are kind of connected to. So when you see this, you just have to think about a little alarm bell going off and say you have an external power source connected here to your battery. So that's kind of what I just tried to redraw up here, showing that I had this I'm gonna stop sharing that, this electronic power source, and for some reason it's just bringing up this. I apologize. There we go. I wanted to make sure you see that it's a battery. So this is about electrolysis. So a couple of notes I wanted to emphasize. Electrolysis is a common method of forming pure elements from a compound. The compound they gave us in this problem was magnesium bromide, and they used this word called molten. And if you're unfamiliar with that word, all that means is that this solid salt, as any solid salt is at room temperature, has been melted to create its liquid form. So when you see the term molten, you should realize that it has indeed just been liquefied so that electrons can flow. So in the molten form, it's been liquefied. It's not dissolved in water, but rather just a liquid bath of magnesium bromide. Notice the external battery so that you can see that this is non-spontaneous in the forward direction. You have to force this reaction to occur. And as a little side note, remember that galvanic cells, also called voltaic cells, are spontaneous in the forward direction. So you don't see this external battery. So what we're now noticing is that this particular electrolytic cell, because it has this battery hookup, you're seeing, okay, this is non-spontaneous in the forward direction. We have to have some external electromotive force forcing this reaction to occur. A voltaic cell, you'll notice that they'll have two different beakers, if you will, an electrode in each and a voltmeter attached to them. So a kind of a visual clue that a galvanic or voltaic cell is spontaneous. You're going to see two separate containers. One is an anode, one is a cathode. In this electrolytic cell, it's the same container hooked up to a battery. Okay, so kind of just thinking about what that means, magnesium bromide in its liquid state is being forced to decompose because this salt isn't going to naturally decompose on its own. You're going to have to force it. And just to review, we're looking at kind of this external force here. The electron flow is heading from here down to potential A. All right, so enough rambling about the visual. Let's make a note. We understand reduction always occurs at the cathode. And reduction at the cathode, remember, I always just think of it as the two constants, the R and the C going together. And heck, I can put this too. Remember, oxidation always occurs at the anode. And those are the two vowels that go together, if that helps you remember. And by the way, that's true for both electrolytic cells and voltaic cells or galvanic. Just keep in mind, I keep using those words interchangeably. They are spontaneous voltaic or galvanic cells. I use those words. So I'm going here. So reduction at the cathode, oxidation at the anode. We know that the loss of electrons is oxidation and the gain of electrons is at the cathode. So kind of think of it in terms of a little bit of where the electrons are going and heading. The cathode, because they are gaining their electrons, think of that as where the electrons are entering the cell. So that the cathode, the site of reduction, remember the loss, thinking about reduction is where you'll have those electrons going into that battery. And then on the opposite here, the anode is where the electrons exit the cell. So gain of electrons going into the cell, loss of electrons coming out of the cell. This molten form of magnesium bromide, I am going to just stress that as liquid, not solid. You can actually think about that as a, you can think of it as, instead of aqueous ions of magnesium, you just think that is magnesium +2, but it's in its liquid form. And you have 2 units of bromide that are in its liquid form. And over here, you're going to form the elemental magnesium and the elemental form of bromine, both in their liquid form. So that's the term molten. Not aqueous ions, but actually taking the salt and melting it. So we can see the elemental form over here in its liquid state. Bromine is one of the naturally occurring diatomic molecules, so that's why we're writing it as Br2. And now I can see some change of charge, recognizing that a redox reaction has occurred. The magnesium, which started as a +2, went to the liquid form of the element Mg. Remember, to balance, we add electrons to the more positive side. So here we can see that this would be called reduction. And the reduction then, remember up here where we said it's entering the cell, the cathode is the site of reduction. The cathode is where they're entering the cell. So going back up to visually see that where they're entering the cell is in that direction. And what about the second half reaction? Well, we had 2 Br negative ions, not in aqueous solution, but as molten, as liquid. And it formed the elemental form there, Br2. And remember, to the more positive side, we balance by charge by adding electrons. So there we have 2 electrons added. Loss of electrons we know is oxidation. And I always take a little shortcut and say Leo and Ger to help me remember which ones they're going to be. So in electrode A, we had the reduction, and electrode B, we had the oxidation. So as I see, your questions in ALEKS are generated individually. So if you have a different salt, it doesn't matter. The question is going to be answered the same way. I saw just a chat question that came up and said, what if I didn't have magnesium bromide? What if I had calcium bromide? What if I had a different salt? Doesn't matter. Molten means that we're going to separate those into 2 half reactions, where a molten form of the 2 ions go and form the molten form of the elements. So your positive or even negative ion might be slightly different, but it doesn't matter. The process of answering the question is still the same. So we've written the 2 half reactions. The 2 half reactions were written up here. You've combined them to form an overall balanced equation, and we've identified electrode A as the site of reduction, which is the cathode, and we've talked about electrode B being the site of oxidation, which is the anode. And that's all of those questions for that particular part. So let me give you a moment to just process that. You can ask a question. Give you a minute to just kind of think about any questions before we move on. All right. There, now I have it back to full screen. All right, so let's move on. I didn't hear anything or see anything chatted. Here's the next question in your ALEKS. This one is asking us to write a balanced half reaction for the oxidation of bismuth, which is Bi3+, and turning it into the bismuth oxide ion in an acidic solution. So this is just practice writing a half reaction. So together, let's go ahead and write that I have bismuth, which is starting as a 3 positive, and I know it would have to be in an aqueous ion to be able to have a charge. And I'm going to point at the bismuth oxide, which is BiO3, and now it's a -1. And we're doing this in an acidic solution, which we understand has a little different twist at the end if it's a basic solution. So our steps will say, number one, balance all of the elements that are not oxygen and hydrogen. So as I just review those steps, balance all elements that are not O or H. And that particular step is done. 2, we know to balance the oxygens next by adding water to the side that needs more oxygen. So let's take care of that step. Here I notice that there are 3 oxygens on the right and there are none on the left. So I'm going to begin by balancing the oxygens by simply adding 3 units of water. So the O's are balanced by adding water. Step 3 says, now balance the hydrogens. And we're going to do that by adding protons. Protons are what we call hydrogen ions. So notice on this side, we have 6 units of hydrogen. So to the right side, I'm going to add 6 aqueous ions of protons. So there I have 6 H+. The 4th step is to balance charge by adding electrons to the more positive side. So let's see where we're at so far. On the left side, I have a total charge of a +3 coming from the 1 unit of the bismuth. And over here, I have 6 units of a +1 with a -1. So that gives me a total of +5 as the charge on the right. To the more positive side, we are going to add electrons to balance that. They both don't end to be 0, they just have to be the same charge. And so when I add 2 negative electrons, I now have them both balanced with a +3. We've balanced by mass, which means each element is the same on both sides. We have the same number of bismuth, the same number of hydrogens, the same number of oxygens, and we've balanced by charge. So with redox, we know that we have to have it balanced by mass and by charge to be an electrically neutral, the same number of electrons flowing from both sides. And that's really all there was to this particular ALEKS question. We didn't have to add them all back together. We just simply balanced a 1/2 reaction. I knew it would be oxidation, so I knew that there would be a loss of electrons, kind of a word clue there that the electrons would end up being on the right side of that equation. All right, let me give you a moment to think about that. See if you have a question. Feel free to either turn on your mic or plunk it into the chat. I'm all good. Good. Well, let's keep going. I have a next question. This one looks a little overwhelming, so let's kind of take it slow. It says a certain half reaction has a standard reduction potential. So I'm just given here a standard reduction potential of -0.66 volts. An engineer proposes using this half reaction at the anode of a galvanic cell. So when I see galvanic, you know that it's spontaneous in the forward direction, no external force is needed. And it has to provide at least 0.5 volts minimum of electric power. So now we're asked, the cell will operate under standard conditions, that's fine. What is the minimum amount of energy needed from the other cathode in order to make this reaction work? So just kind of thinking about what it's asking. we have this cell that it needs to provide a certain minimum amount of energy. And I know that to calculate the standard cell, the value in volts, we take the standard reduction at the cathode and we're going to subtract it from the anode. So I just remember always put the C's together. The E cell standard is found by subtracting E cathode minus E anode. So if we need a 0.5 volt minimum, and at the anode it's saying that what we were given is a negative 0.66 volts. That's what this is saying here, that the standard potential E reduction is negative 0.66. What do we need right here to generate this positive voltage and have a spontaneous reaction? Now, I knew to put this value, I need a more positive value, right? I have to end up with a positive sign to have a spontaneous reaction. So let's just solve this right here. I have 0.5 volts set equal to whatever the volts at the cathode must be, minus negative 0.66, whoops, I'm sorry, minus a negative 0.66. So that's really saying plus 0.66 volts. So 0.5 minus 0.66, bringing that over to the left side, is going to give us the cathode value at a minimum to cause this spontaneous reaction. And if I subtract that, I get a value of negative 0.16 volts. That must be at the cathode to have a spontaneous reaction occur. So just double check what we've just done. We needed a 0.5 volt. If I had a negative 0.16 volts at the cathode and a value of negative 0.66 volts at the anode, I end up to have a spontaneous reaction with a minimum of the 0.5 volts that we were targeting. So here is the minimum voltage we need at the cathode to cause this reaction to meet the criteria. So yes, there's definitely a minimum that you need to supply at the cathode, and that minimum was negative 0.16 volts. Theoretically, there's no maximum value at all. I mean, if you think about the standard reduction table, theoretically, it could go to any high value, but we're limited to what we see on the reduction table. So just to kind of clarify, theoretically, this could keep going and be any positive value, but realistically, we kind of stop at just about 3 volts. So with that particular question is, theoretically, there's no maximum, but realistically, there truly is a top to the voltaic reduction table. And then it says, by using ALEKS data tab, which you'll open up, the little bar graph to find the standard reduction table, it just simply asks for a balanced equation that could be used to meet the criteria. So I just kind of screen captured where we were at in terms of our value being negative 0.16. And notice that you are somewhere directly in this particular ballpark of the reduction table. So technically, any answer that would provide a spontaneous reaction would be fine. I know that I just selected the one that is closest to it because it looked like the easiest choice to write. So I would say an example would be the tin plus 2 ion in reduction forming the element tin. And that would be an example where I would meet the minimum to cause the reaction to be spontaneous. But any of those answers would be provided as well. So there's no one correct answer to that part of ALEKS. A minute to think and see what you have as a question. How you doing out there? It's awfully quiet.
So the value you could put in for an answer anything above that negative 0.16 volts.
That's correct. Yep. So that's what I mean is there's no maximum technically. If I could find other elements, I could probably find more value up here. You know, when I said right about in the area of negative 0.016, you could pick any of the answers that lie above. So I just picked the one that was right in that line, but I could have written any of those equations and been correct. I see in the chat, how do I know there's no maximum again? Just simply because theoretically I could have, you know, a voltage of any number. It could be high, it could be low. So theoretically there is no maximum, although I'm just saying realistically, there are only so many voltaic cells out there to have, you know, specific electrodes that work. We're limited to what we see on the standard reduction table to these half reactions. But notice that as I crept up to the highest, the fluorine, 2.87, could there be something with even a higher voltage that we just don't know of yet? Probably, maybe, but at this point in time, we're limited to what we see stamped on our reduction table. So I think that's why they said, is there something theoretically, could there be a standard reduction? So realistically, there is a maximum, but, theoretically, that table could go on. Darius, you can turn on your mic if you have a question.
I do. So, if we had this reaction, like the same thing, but the last question was asking about the reaction if it happened at the anode, what would we do to that chemical equation?
So if your value, I did put mine at the anode here. You're just considering then if that reaction needs to come out with a 0.5 value and a half reaction at standard reduction is given as negative 0.66, what value can you add to turn that into positive 0.5? And so it's really tackled the same way. You're just trying to make sure that no matter how you answer, those two values come out positive.
Thank you. That helps a lot.
Okay, sweet. All righty. Let's take a look at a next one. This is just a little quick problem I saw that was a smidge different than the last half reaction. This is question 4 off your ALEKS, only because now we're being asked to balance in a basic aqueous solution instead of an acidic solution. So we're still writing a balanced half reaction, the oxidation of liquid water. So I'm just beginning by writing liquid water, and I'm going to point at hydrogen peroxide, and we're just being asked now to balance it. So really, the same steps occur, but with a little twist at the end to neutralize the protons. So let's begin. Step number 1, balance everything that's not an H or an O. Check, that's done. Step number 2, balance the oxygens first by adding water to the side that needs more O. So with that particular step, since we have 2 oxygens on this side, I'm going to add 1 more water over here to have 2 oxygens on the right side. I'm sorry, on the left side. So 2 O's on each side. Our next step says balance the hydrogens, and to do that, you add protons to the side that needs more H. And when I say protons, you're just thinking of hydrogen ions. So on this side, I'm counting 4 hydrogens. On this side, we already have 2. So that means I have to add 2 more protons, and that little adjective will be aqueous. Water is a liquid there. So we've got the H's balanced, we've got the O's balanced. We now consider charge. On the left side, I don't see any charge at all. So I write 0, and over here we have a +2 from the 2 protons we added. So to the more positive side, I'm going to add 2 electrons to balance charge, which is good because they told me it was an oxidation half reaction, so I know that they're going to come out on the right side as products. Right now, we could be done if it said acidic solution, but it didn't. It said basic solution. So the last step says what we need to do now is to neutralize the protons by adding the same number of hydroxides to both sides to neutralize. So when I see on here, I have 2 hydrogen ions. When I mean to neutralize that, I got to add 2 units of hydroxides. But just like in math, what I do to one side, I've got to do to the other to keep the equation balanced. This now, when they neutralize, is forming 2 water molecules. So 2 H's and 2 OH's neutralize to form 2 waters. When I look at what's on the left side, I have 2 waters on the left. I made 2 waters on the right. They're going to simplify by canceling each other. So these 2 OH's cancel the 2 OH's, or the 2 waters on the left cancel out the 2 waters formed on the right. So to just rewrite what we have left, I have 2 OH negatives, which would be aqueous ions, forming H2O2, which is aqueous. And coming out also, we have to remember the oxidation half reaction would have 2 electrons on the right side as well. So that reaction has been balanced by mass, by charge, and neutralized for the basic solution it was run in. So even though that was a little shorter one, I wanted to model a basic solution as well. What do you think? No one's yelling, so that one went well. Again, feel free to turn your mic on, interrupt if you need. My dog is sneezing in the background. That one went well. There's a series of those, so maybe I'll choose to not do question 5 to focus on something different if that one felt okay. If you look at this question, ALEKS 5, do you have an idea of how to get started? I can see that I would separate the 2 halves, balancing the 2 half reactions and then adding them back together. Well, why don't I just go ahead and quickly do that? I'm going to point H2 at water, and I'm going to point copper +2 to copper +1. So I just separate the 2 half reactions. I'm going to balance both halves. I am in a basic solution, so I want to make sure I take care of protons. Let's tackle the first half reaction. I need to add water to balance the oxygens on the left side. So I have 1 O on each side. That makes me have to balance hydrogens over here. So I have 1, 2, 3, 4. I need 2 more protons on this side to balance the H's. And that also means I better add 2 electrons to balance by charge. So the first half reaction balanced by mass and by charge shows me a water plus hydrogen making a water plus 2 protons and 2 electrons. Down here, this one is quite simple. I just need to balance by charge, and so I can quickly do that by adding 1 electron to the more positive side, so they're now both balanced equally by charge. Remember to consider that if 2 electrons are lost and 1 electron is gained, we have to make sure that Leo equals GER, right? that the electrons lost must equal the electrons gained. So if I have 2 electrons being lost, but only 1 gained, I have to distribute a 2 through that second half reaction to make them balance for electrons. So when we add back together, I'm going to add everything on the left side, H2, H2O, and 2 copper plus 2s, and 2 electrons, pointing at, now back up to the first half reaction, we have a water, we have 2 protons, 2 electrons, and on the right side, we have 2 copper plus 1s. So I added back together and distributed the 2 through that second half reaction. What can we simplify? The electrons are gone. Looks like we have a water molecule that can go. And that's it. Remember that copper plus 2 does not cancel a copper plus 1. They are different from one another. We need to neutralize the charge of the protons by adding 2 hydroxides to both sides because we're in a basic solution, so that this will neutralize to form 2 waters, and the left side is left with the hydroxide, and that has to be 2. My bad. So I think we're ready to just write it out. Here we have a hydrogen, and it would be 2 aqueous ions of hydroxide with 2 copper plus 2 ions pointing at 2 waters, which is liquid in the form there, and what's left, 2 copper plus 1 ions. That looks like separating, getting them balanced, and putting them all back together, and with that little twist at the end, making sure you remember to neutralize protons. How does that feel?
I was a bit confused why we didn't add the H2 with the OH, but I realized it's because H2 is a gas and OH is aqueous, so you can't make them a water.
Oh,
So,
great,
that was-
great observation. Yes, thank you. Yep, hydrogen gas kind of started us up here. Yeah. Good, good. Okie doke. All right, so I'm going to skip a little bit to number 8. And I did that because it's just one of these, type of questions where you open up the data tab and you're asked to rank the following ions. Well, one of them is liquid bromine. Just ranking them in terms of their oxidizing power. So when you see oxidizing power, I just want you to kind of in your head going, okay, what they're really saying is it's a oxidizing agent is another way to say that, which is the one we know that's being reduced. So I wanted to just kind of clarify some of that vocabulary. I also just kind of opened up the ALEKS data form, and I just grabbed some of these, the standard reduction from the table here and kind of highlighted where I'm finding those numbers. And so I noticed that, for instance, liquid bromine had a 1.09 volts stamped on the table. Underneath that was silver, which was 0.0 or 0.80 right there. And then for nickel, that was negative 0.26. And then the last one, aluminum, was negative 1.66. So all I did was kind of do that hard work of looking at the reduction table and pulling out their values. But really, once you see them listed, the strongest oxidizing agent is at the top, and then the second, and then the third, and then the fourth. So the strongest oxidizing agent is the one most likely to be reduced. And so when you numbered those just straight off the table here, Bromine was ranked first, silver was right underneath it, and then next would be nickel, and then finally aluminum, as it's the lowest, most likely to be oxidized rather than reduced. So that one, when we kind of chat about strategy, it becomes simple, but I didn't want the word oxidizing power to kind of throw you. So I wanted to grab those vocab and say, if you're asked about oxidizing power, it's oxidizing agent. And so really in your head, it's saying which one is most likely to be reduced. And that's the one at the top of the table. I wanted to show a galvanic cell. I know the first problem that I had was an electrolytic cell. This is a galvanic cell, which just means that it's spontaneous in the forward direction. There is no external battery, so I can realize that I'm going to have positive volts for E cell. So thinking about what's going on here, I have two separate containers. One will be the anode, one will be the cathode. I have two separate electrolytic cells going in here. One will be the anode, one will be the cathode, and they're connected to a voltmeter, and it will be a spontaneous reaction. I'm going to take this equation, I'm going to rewrite it and just throw out the spectator ion of nitrate. I don't like the spectator in there. I know that nitrate is, well, I'll put it right in here. I know that nitrate is in both solutions. I know that because it's a spectator and it's just floating there, minding its own business, doing nothing. But the chemistry of the redox is starting with solid iron and having it react with an aqueous ion of lead-2. And it's pointing at now an aqueous ion of lead-2, and the solid lead has been formed. So iron started as solid, ended aqueous. Lead started as aqueous, went solid. So here I can see that the oxidation occurred from iron and the reduction occurred from lead. So I'm just eliminating the nitrate is in both containers. I know it's a galvanic cell. Remember that oxidation occurs at the anode and reduction occurs at the cathode. So we have to kind of remember, my trick is to remember the two vowels go together. So the anode, the site of oxidation, is where the electrons are going into the cell, right? Notice that the spontaneous reaction is bringing those electrons here. So oxidation, loss of electrons, the electrons are being lost and entering the cell on the left side. And therefore we know that this is the site of the cathode, which is where the reduction occurs. And that positive volt is forming as it leaves the anode, goes through the voltmeter and comes back out. And remember, this is what we just called the salt bridge, which completes the circuit. Alrighty. So where the electrons enter the cell and where the electrons leave the cell can help us determine those reactions. To separate the two half reactions, notice that you will have iron as a solid going to the aqueous form, and to balance by charge, you'll have +2. And then over here, the half reaction for reduction would add those two electrons, forming the solid form of lead. So there's the two half reactions. Loss of electrons, oxidation. So we know that that is happening at the anode. And gain of electrons is reduction. So we know that that is happening at the cathode. What else is it asking? So just to kind of make sure we see in this solution here, you're saying iron is forming iron +2 and 2 electrons, oxidation. So what's in the solution here is the aqueous ion of iron And don't forget, there's an aqueous ion of the spectator as well. Both are in there. And what's in solution over here would be the aqueous ion of lead. And of course, the spectator is also on that side. So the aqueous ions of iron and nitrate are in this solution, and the aqueous ions of lead and nitrate are in this solution, meaning that this electrode here, that's the solid iron, and this electrode over here must be the solid form of lead. So just kind of splitting those two apart helps us kind of go through each one of those components and kind of track flow of electrons. Thumbs up, good. And I'm just pausing to make sure you have time to write, think, and ask a question before we show a next slide. So if I'm just quiet a moment, it's just to give you think time. Oh, I see a question. Electrode 1 and 2 are solids. That is correct. Yes. You can see them kind of in the picture. They have a little cap on with a wire. If you see like a chamber that would have gas in it, that would be an inert electrode. You know, really good question is, even back in this first question, this was considered to be an inert electrode because they're made of graphite, which is just kind of like pencil lead carbon, which is not part of the chemistry going on. Notice that the magnesium chloride is not building either one of those electrodes. So that vocabulary word there is just said to be inert. Since these electrodes are part of the chemistry, they're solid forms of the ions in those solutions, they are actively involved in the redox reaction. Maybe I'll end one with a calculation then. Here's one that asks us to consider a little calculation about running a charge through a period of time and calculating either mass or electric charge that comes out. So with this question, it comes from 23 on your ALEKS. It's given me 15.60 amps and it flows for 30 minutes. What we want to know is the amount of electric charge that was transported, and then just report your units with 3 sig figs. What I wanted to highlight is just thinking about the very definition of the term amps. Amps is defined as coulombs per second. And the SI unit for electric charge is a coulomb. So if you are reading a problem that says find electric charge, what you're really being asked is to report your value in a coulomb of energy. The SI, Standard International Unit of Electrical Charge, is a coulomb. So this problem could become quite simple just by looking at what was given as 15.60 amps. But instead of amps, why don't we just rewrite that by saying 15.60 coulombs per second? And then when we set up our conversions, we could just cancel those units by saying, okay, I'm going to run it for 30 minutes. So I know that there are 60 seconds in a minute, and then I know that there are 30 minutes that we're running it for. Minutes canceled, seconds canceled, and when I find this answer, I've just done a little bit of unit conversion and have landed at coulombs. So whatever unit or the values that your numbers gave in your ALEKS number 23, amps defined as coulombs per second, So multiply by the number of seconds that you're running that charge through. When I got my calculator out and hit that, it was 28,080 coulombs. And it said to report to 3 sig figs. So you might want to just reduce, don't have those trailing zeros. So just consider perhaps scientific notation. You could write that as 2.81 times 10 to the 4th coulombs, and that reports in 3 sig figs. Or another idea, you could report as 28.1 kilocoulombs and still have 3 sig figs as well. So either way of reporting would meet the requirement of 3 sig figs there. We have 10:50 on the clock, so that is the end of our required time together. I'd be happy to stay on the line. If you have additional questions for me, feel free to stay. If not, you're very welcome to go, and just remember to submit your notes into the Dropbox. Thank you, everyone. Have a great day yourself. I'll be the last one to leave. So if you have a question, you want to work another problem together, just open your mic and let's chat.
So I have a question. So when you do the final answer with the sig figs, it doesn't matter whether it's coulombs or kilocoulombs?
A great question. And the answer to that is in your ALEKS, it did not provide a unit. Sometimes it does in the box. Like sometimes you'll see a box and it will say K coulomb or gives you a unit here. And so then I have to put a number in that matches the given unit. But in this problem, it did not give me, all I see is an empty text box. So the number I place in here has to have a correct matching unit. And if both match, you will get full credit. So I could have answered, well, I can't answer this way because that's too many sig figs. But I could have typed in either one of those choices, kilocoulombs or just coulombs, with 3 proper sig figs, with it being the proper magnitude, and you'd have it correct.
Okay. If you're like willing, could we do more questions?
Sure. Do you have one in mind, or do you want me to just pick one?
Could you pick one?
Okay. Sure. So you can see on my slide, I have some more ready. Let's see. Here's one that is a little different as well. Let me get my full screen back up here. In this particular question, we're given all kinds of information about 3 different cells, A, B, and C. And this is kind of figure out what it's giving us. A student made measurements on some electrochemical cells, and the cells were just labeled cell A, cell B, cell C. And what they did was to just do some calculations for Gibbs free energy, for the equilibrium constant, and for E cell. And what it's asking us to do is to find any error in the rows. At first, this one looks a little overwhelming because I have so many numbers and so many formulas. And yet, if I understand relationships, this question becomes a little bit easier. Let's talk about what type of relationships exist between delta G, which we know is Gibbs free energy. So when it's positive, we know that the reaction is non-spontaneous in the forward direction. Gibbs free energy must be negative to be a spontaneous reaction in the forward direction. What do we know about equilibrium? Well, the equilibrium constant says, if I have a value greater than 1, I know that the products are being favored. That I have way more products than I do reactants in the container at one time, because equilibrium, remember, is the expression of products over reactants. So if I have more product, that number comes out bigger. And if the equilibrium constant is less than 1, we're actually favoring the reactant side. The reaction is to the left, we call that. And then the third value was our standard reduction for the cell, what we called E cell. And we learned that it must be positive. I must have positive voltage to be spontaneous in the forward direction. And if it's negative, it's not spontaneous. You know, negative voltage isn't going to run a battery, right? So non-spontaneous in the forward direction. So as I look at those relationships, I can kind of look closer at these numbers, and without doing a single calculation, I can find the one that's not correct. Now let's model that with, let's look at cell A. And I'm just going to rewrite what I see so I can have it a little bit bigger. In cell A, the delta G is given to me as negative 126 kJ per mole. The equilibrium constant is given to me as 8.43 times 10 to the negative 23. And the E cell is given to me as positive 1.31 volts. So which one of those of the three is wrong? So what I look at in the first one, I have a negative delta G. And remember, that's saying to me that a negative delta G is spontaneous in the forward direction. And E cell, because it's positive, says it's spontaneous in the forward direction. So that's what I mean by pointing this way. And yet what's odd is this really, really, really tiny value of K. Since I'm noticing that K is less than 1, it's a really tiny number. What that tells me is that this is favoring, oops, I can spell and talk, I swear. This is favoring the reactant side, this side of the arrow. So when I look at this, the magnitude of the numbers, are they negative? Are they positive? Which one of these seems to have an incorrect calculation?
The K.
Yeah, you're exactly right. The 2 of the 3 are telling me the reaction is pushing forward, and yet the K value is telling me it's not. And so that one is suspicious. And we could calculate that pretty quickly just to verify. I mean, just to remember that delta G is negative RT LNK. That's our equilibrium expression. So, you know, just very quickly, you could say, you know, calculating that out, negative 126 is our delta G value. 8.31 over 1,000, because I have to have that in a kilojoule. And that temperature would be 298 Kelvin, LNK. And I just happened to do that earlier just to kind of prove it to myself. So I wouldn't just expect us to know that by heart, but I just kind of simplified. When I found all of that out, I solved for K, and it came out to be 1.25 times 10 to the 22. Notice when it's calculated properly, how large that number is, which would favor the forward direction. So without even having to calculate anything, I realized that that's the odd guy out, because the other 2 are telling me forward direction. That's the one that's odd compared to the other 2. You can prove it to yourself through a calculation, or you could just spot it based on understanding those relationships. Each one of those is going to have one of them that doesn't match. Does that make sense?
Yeah, that does.
Great, great, great.
Besides that, I don't have another question.
Alrighty. Yeah, these are just I guess the other ones I grabbed are, I have just another practice with some voltage and practicing half reactions. The remainder I have done examples of. These were just more examples of the same.
Okay.
So
Well,
yeah, I would say you've got a few days to look it over, and if you certainly do have any more questions on ALEKS or anything else in general, please just reach out.
alrighty. Well,
Yeah, and what I'll do, of course, yeah, I'm going to turn our recording off.
okay.
Yeah.
Have a good one.